Out here, where time is money, improving drilling performance starts with the integrity of the drill string. A recent worldwide survey puts the cost of downtime to the industry at $31 billion, with downhole failure as a significant percentage. Since vibration and high shock loads are a major factor in downhole tool failure and can also cause rig repair and hole problems, prevention is a very high priority. When you look at these obvious consequences of drilling vibration and high shock loads, it's not surprising how much you can boost overall drilling performance when you use a proactive approach to preventing or reducing these destructive forces. Since the first step in solving a problem is giving it a name, let's focus on how we describe these forces. There are three modes of vibration: axial, lateral, and torsional, which are the directions the drill string moves when it runs into trouble downhole. In the axial mode, the vibration is longitudinal motion along the drill string, resulting in varying tension and occasionally compression-tension reversals. In the lateral mode, the vibration is side-to-side motion that causes flexing or bending of components, again leading to stress reversals, where one side of the pipe will be in a different tensional state than the other. In the torsional mode, the vibration is resistance to rotation, resulting in twisting as torque is applied to overcome resistance. So that's how the drill string reacts if it runs into any of the 9 different kinds of trouble we call vibration mechanisms. The first one, called stick slip, is irregular drill string rotation. The vibration mode is torsional, as the bit stops rotating momentarily at regular intervals, causing the string to periodically torque up and then spin free at 2 to 15 times the average surface RPM, causing severe damage to the bit and BHA. The second mechanism is called bit bounce. It's the axial or longitudinal vibration of the drill string that typically happens with 3 cone bits in hard rock formations. Bit bounce damages the drill bit cutting structure, bearings, and seals, and results in flexing of the drill string, causing even more damage from axial and lateral shocks. Next is bit whirl. It occurs when the bit has cut itself a hole larger than its own diameter, allowing it to wander around in the wellbore instead of simply rotating around its natural center. Excessive side cutting creates an overgauge hole that, in turn, increases the tendency for the bit and BHA to continue whirling. Number 4 mechanism is BHA whirl, the eccentric rotation of the BHA around a point other than its geometric center in a complex motion, generating lateral displacements, shocks, and increased friction against the wellbore. Occurring as forward or backward whirl, it's the mechanism that constitutes the main cause of BHA and downhole tool failure. Next, lateral shocks describes what happens when the vibration mechanisms of bit bounce, BHA whirl, or modal coupling become so extreme they cause the release of energy built up in the drill string through sudden large lateral shock impacts. Unlike BHA whirl, where the motion settles to a steady state, in this case, the lateral shocks occur randomly. Torsional resonance is specifically drill collar torsional resonance and causes a juddering vibration of the drill string. It typically occurs in very hard rock being drilled with a PDC bit. Parametric resonance is our name for the severe lateral vibrations generated by axial vibrations caused by the interaction of the bit with the formation, which results in fluctuations of weight on the bit. Bit chatter is the high-frequency lateral and torsional vibration of the bit and BHA, caused by slightly eccentric bit rotation where there is cutter interference with the bottom hole cutting pattern. The cutters ride up onto the ridge between previously cut grooves and then drop back into the groove. Modal coupling describes vibration occurring in all 3 modes, axial, torsional, and lateral, simultaneously. It creates axial and torsional oscillations and high lateral shocks along the BHA. The most extreme form of vibration, it usually results from failing to control one of the other vibration mechanisms. Okay, now that we've identified the problem, what are we going to do about it? The solution starts with sensors that are able to measure the different modes of vibration and enable us to identify the different mechanisms. Accelerometers can be mounted in tools to measure axial and lateral shock and vibration. Sensors that measure changes in downhole rotary speed and changes in torque at surface can be used to identify torsional vibration. Sperry Drilling Services' extensive experience with our wide range of vibration tools has proven that with all the factors and variations that affect vibration, real-time monitoring is the key to managing the problem. We also offer software that provides an automatic recalculation of the natural and harmonic resonant frequencies of the BHA. This is based on change in weight on bit, hole angle, dogleg severity, hole size, and mud weight, and reflects the actual drilling conditions encountered. All of the critical RPM values can be displayed at the rig floor, so this form of vibration can be minimized. A vibration monitor analyzes measurement from the downhole tools, can automatically determine the vibration mechanism, and provide advice on changing drilling parameters to stop it. Of course, measuring and responding to the complex array of vibrations while drilling is a real challenge. That's why Sperry provides specialists from the Applied Drilling Technology Service, or ADT, to help you determine the vibration mode and mechanism that's causing your problems, and come up with ways to mitigate it. The ADT Optimization Service will also identify ways of preventing the vibration from occurring on subsequent bit runs or welds. By modeling the expected conditions and making the correct measurements while drilling, we can virtually eliminate vibration. This significant step toward optimizing the drilling process can save the industry a huge chunk of the $31 billion cost of downtime. For more information, please contact Sperry at Halliburton.com.